So let's start with design of experiments based on the randomization process. So the way this process works is that we imagine we have two parameters, temperature and time, duration of heating, and we want to see how this is related to strength. And we want to see, imagine, in some ways, we have identified that the temperature is more important than the duration of time. And also imagine that we are not controlling time very accurately. So we have high uncertainty in time, but we can control the duration of curing, but we can control the temperature of curing very well. So now let me share with you my white board here so that you can get a better feel of what I'm talking about. So imagine this is the y-axis is the strength that I'm measuring, and the x-axis is basically the temperature of curing. And the y-axis is the strength that I measure, from each sample. Now, let's say, before we understand randomization, let me give you another curve that I would call the ideal experiment. Let's say, based on an ideal experiment, I know that the strength varies like that with temperature. So here we are talking about 100 degrees C, and we have another point here that the best case scenario happens, which is let's say 170 C, and after that the strength basically drops if you further heat it up. So for instance, in this last case, let's say the temperature is 1200 C. And imagine in all of these cases, this is the ideal case that I call the ideal case. Ideal case in which the time duration of curing is exactly 3 hours. Okay, so in the randomization process, we don't know this curve. Okay, we don't know. We want to get it from the experiment. Now let's say I have another sample. Now I design my experiments based on randomization. I make, let's say, 10 samples. So I sort them out here in all of them. So this is sample oops, sorry, my axis just went away. So and so in all of them, I call, this is the first one is the sample number, the second one is temperature, the third one is duration, and the fourth one is T. In this axis, I put a giant question mark because in my real experiments that I'm going to show with blue, I don't know that. So I have my sample 1, 2, and all the way to sample 10. Temperature, let's say one of them is at 100, it's in C. One is 120, there's another one, 110, there's another one, this is 180, and there's one before that, that's 200, and so on and so forth. Then there's somewhere in between. And in each of them, I measure strength, okay? So for instance, the strength of sample 1 will appear somewhere here. It doesn't appear to be exactly on this curve because the duration, this curve is only for 3 hours, and the duration I have is unknown. So it could be different. Because of that, it doesn't happen here. I have another sample that it perhaps happens to be here. I have another one here, 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 another one here. So if I fit a curve to all of that, I can probably get a curve that more or less looks like this. It doesn't exactly fall on the black curve, which is the ideal curve, but this is the curve that is made through the process of randomization. Basically, what we're saying is that the variation in this temperature, the variation in time, the duration of curing, is so random that is not affecting my the average behavior of my experiment. Now, so here we are assuming that this is random. Just to tell you what I mean exactly by being random, imagine the case where I didn't have a random variation in time, but I had a systematic difference. Let's say in all of them, basically in the case of random, I'm assuming they are spread around the 3 hours. One of them is, this could be, for instance, 1 hour. This could be, let's say, 4 hours. This could be 3 hours. This could be 1 hour, 2 hours, something like that. Now, let's say, or let's say here 4 hours. Let's say in all of them, this is randomly distributed time. Now, let's say instead of that, in all of them, the time was off. All of them were at 1 to 2 hours. Then instead of this blue curve, I probably would have gotten something like this. In this case, T is not random around 3 hours. It's always less than 3 hours. So this is not a randomization experiment. What we call the randomization is that the variable that we are not controlling, in this case T, is randomly distributed around the values that we are interested in. In that case, we can ignore the changes in that and still get the trend that we expect from the experiment by looking at the other variable, in this case T, which has a more impact on the experiments, on the output, which is time, which is strength in this case. So basically, we are assuming an independent and random distribution of a parameter, which in this case is the time. And the average behavior that we get, that blue curve that I showed you, is averaging out the effect of randomization in the parameter of T. The other case is that if T was not random, we would have bias, like the yellow curve. But in this case, because T is random, we can reduce the bias in the measurements. And so this is, you can map this to the experiment we did. So here, this treatment is just the temperature because T is random. Okay, and so we have high temperatures, low temperatures, intermediate temperatures, and different levels. So here we're assigning treatments temperatures randomly to samples with different times of curing, and we run the experiment. So the treatment here is temperature that is randomly assigned, that is randomly coupled with duration of heating, that is a random variable, let's say between 2 to 4 hours, or 1 to 5 hours. So we're gonna stop this video, and we're gonna continue on the